No pressure. My turn now to save the planet. Thank you, Ram. I've been told not to talk about all the great things that Ram has done and how he's led this field and inspired so many of us. I'll just let that be implicit in my talk. But thank you for that, Ram, and congratulations to such a well-deserved honor. So I worked with Ram as a postdoc, and we worked on storm track clouds, and that's these clouds here that you see in the mid-latitudes in both hemispheres, whoops, up here where we live, and they have this swirly character, very characteristic. These clouds form when cooler and warmer air masses meet, and low-pressure system cyclones are formed on these fronts, and air rises and cools, and clouds form and precipitation falls. As you can tell, that's not the only cloudy region. We have these clouds, but where Ram lives, in Southern California, over here, that's also a cloudy region. And I remember when I was at Scripps that we got to bet, you weren't part of this, Ram, but we got to bet on how many days the June gloom would last. So the June gloom is the days of very overcast skies in this area in early summer. So the reason there's clouds here is that we have ocean upwelling, a cold surface, and we have subsiding air above, and this keeps a very steady cloud cover in this region, this stratocumulus region. Oh, this one's hard. California region, and also similarly off the coast of South America, and also off the coast of Africa and Australia. Yes, there are lots of different cloud structures, and Sandrine went through many of them too. Actually, 70% of Earth is covered by clouds. And clouds modulate the surface temperature. They primarily cool the climate by reflecting incoming solar radiation, but they also have this competing warming effect. So it's just like greenhouse gases. They trap the outgoing long-wave radiation. The clouds, they change from day to day. We can see that by just looking out the window, but they also have slower changes. They change with human activity, and this matters. So imagine we had no clouds, and we've already heard this number, 20 watts per square meter. That's how much warming that would give. It's 5 times what the energy balance difference would be from a doubling of the CO2 concentration in the atmosphere. So just a 10, maybe 15% change in cloudiness has roughly the same magnitude of effect on the Earth's energy balance as a doubling of the CO2 concentration. So what the clouds do matter, and I would argue against Ram that the clouds haven't changed much and aren't about to change much. So let's take a look. So clouds are also sensitive to their environment, and changes in cloud amount and cloud properties in turn matters to that environment. So we have a cloud feedback like this. So the temperature changes, that changes the clouds, and that in turn changes the temperature again. So if a warming changes clouds so that you get even more warming, that's a positive feedback. If the temperature changes the clouds so that you get cooling, that's a negative feedback. And I like to say that there are 3 basic mechanisms for this. There's amount, altitude, and opacity of clouds. So if we start with amount, clouds, like I said, reflect incoming solar radiation. So if we change the amount of clouds, we'll change how much they reflect. So less clouds will cool less in general. The altitude of the clouds matters because higher clouds are more efficient in trapping long-wave radiation. So they have a stronger warming effect. So if the altitude of the clouds changes, that will change how much they contribute to warming. The reflectivity of clouds, or the opacity, that depends on both macrophysical and microphysical properties, and this can also change with climate, and thereby affect how much the clouds reflect and how much they cool the surface. So these are the basic principles for cloud feedback. And the total cloud feedback consists of a combination of all these different effects in different cloud regimes. So I'm going to show you here a summary based on the latest assessment report from the IPCC, some updates that I have made to that figure. But we can look by latitude at how different cloud types respond to warming. And we find in the tropics, primarily, actually more broadly than that, but mainly in the tropics, cloud tops are rising. And like I said, that has a warming effect. That's a positive feedback. The thin anvil clouds that surround the deep deep convective clouds in the tropics particularly, they're reduced in extent, just like Sandrine talked about, but they're also thinning. There are studies showing that. So this, we believe, results in a net weakly positive feedback, but it's uncertain and it's small. In the subtropics, again, Sandrine mentioned this, but cloud cover is reduced here. This the result of several different processes, has to do with how strong the subsidence is, how fast the temperature decreases with altitude, many different things. But there is a decrease in cloudiness there, so that's also a positive feedback. In mid-latitudes, there is a negative feedback when warming makes ice cloud more liquid, and that makes the clouds more reflective. If you have the same amount of condensate, if the cloud is liquid, it reflects more than if it is ice. So this is a negative feedback, but taken together, the cloud feedback is positive, we think, but small. And it's also uncertain. So it's in fact the greatest contribution to uncertainty in total feedback in the climate system. And this matters because the magnitude of the feedback determines the sensitivity of the climate to external forcing. So if we want to know how much warmer it's going to get, given a certain amount of CO2 increase, we need to know the sensitivity. So like I said, Ram and I together studied storm track clouds, and what we found was that these clouds shift poleward in all ocean basins in both hemispheres. So what we see here is cloud fraction in color, and it's 4 different ocean basins, and how it changes. Here's latitude and here's time. And so the darker red colors are more cloud fraction, and we have these linear fit lines to guide your eye a little bit. We see that the greatest cloud cover is shifting towards the pole in all cases. And this could potentially result in a positive cloud feedback. If you move the clouds away from where there's more insolation, that could mean more warming, more absorbed solar radiation. Now, later studies have shown that this is probably compensated largely for by other cloud types, but there is still this general tendency over the satellite era of poleward shifting storm tracks and storm track clouds, and a widening of the subtropical subsidence zone. So this cartoon here shows a reference case, and then in a warmer climate we have a wider subsidence zone and storm tracks shifted poleward in both hemispheres. And Ram said I hadn't updated him, so here's an update. George Silotis, who was also on our paper from more than 10 years ago now, recently did an update using more satellite data and looking at longer time periods and seeing support again for this shift. So what we see here is trend in cloud cover in % per year, and we see at the lower latitudes there's a general decrease, and at the higher latitudes there's general increases. So again, supportive of this poleward shift of the storm track clouds. Okay, so this had to do with changes in cloud amount, but as I mentioned, cloud opacity or optical thickness is another important factor. So in this study, we looked at mesoscale cellular convection that Sandrine also mentioned, that clouds have different shapes and morphologies. So a certain cloud type can look different like this. So here we have what we call closed cells and open cells and disorganized cells that are all classified as mesoscale cellular convection. And what we find is that these different categories that we can classify with the neural network approach, they have different reflectivity for the same cloud fraction. So here we see albedo, or reflectivity, as a function of cloud fraction. And we see that these closed cells, they have the highest reflectivity for a given cloud fraction, followed by the closed and the disorganized. And what we then find is that this morphology is dependent on temperature. So with warming, we transition in many areas from the more closed cell to other morphologies, meaning that we lose reflectivity, and so we lose a cooling mechanism. And we can quantify this contribution to positive cloud feedback and find it to be a little less than 0.1 watts per square meter per Kelvin. And we can compare that to the total cloud feedback that is, we think, somewhere between 0 and 1, maybe 0.5. So this is not insignificant. So the purple areas here in this map are regions where the fraction of closed cells decrease with increasing temperature. And the red colors in this map here show positive feedback then. So here we used a machine learning approach to classify different morphologies in one specific cloud category, this mesoscale cellular convection. We can also use neural networks to classify more broadly at larger scale. So what we did here is we determined cloud type from top of atmosphere radiation satellite images that are low resolution, and we classified them into classes corresponding to types recorded by human observers. So we divide into cumuliform, stratiform, middle, and high clouds. So if a satellite image looks like one of these, we can categorize them into what a person would see as one of these categories. And we can then do the same kind of classification in global models. And doing that, we can look at how the different classes change with warming in those models. And we can confirm that models with increasing high clouds, these warming clouds, they have more positive cloud feedback and higher sensitivity. And the models that have more increasing low and stratiform clouds, the more cooling clouds, they have less positive cloud feedback and lower sensitivity. We can also see that the models that have the smallest bias in classification, they are those with more positive cloud feedback and higher sensitivity. So this can work as a constraint then on climate sensitivity. So in this respect, higher sensitivity models seem to be the ones that agree better with observations. So here we see the error in this classification. So the error is smaller this way, and here is climate sensitivity, and these are all different models. So the models with the smallest errors are the ones with the highest sensitivities. Another helpful tool and recent development is storm resolving climate models. So if you think of a climate model grid, just like this, and you think of refining that grid and making the resolution better, you can imagine you can capture more detail. So this is what is going on now in the climate modeling world, that we go to higher resolution. So storm resolving models are global models that have high enough spatial resolution that they can resolve convection. So we can turn off the parameterization of convection in these models. This is really a big step, because these parameterizations, they introduce large uncertainties. They're not necessarily physical, and we'd rather just represent the physics explicitly. Of course, this is computationally expensive, but we're at a point where we have that computing power available. So this is work by Alejandro Uribe, and it's ironic, isn't it, that this plot comes out with a really poor resolution when I'm talking about high resolution modeling. But what we see here is we're comparing ICON, global storm resolving model, at two different resolutions, 5 kilometer spatial resolution and 10. And we compare them, these models, with these traditional CMIP models that have a resolution of the order of 100 kilometers. So what we see is cloud feedback in shortwave, and long wave and net over here. And we see that there are actually a lot of similarities. So between the 5 and 10 kilometer resolution versions of ICON, the differences are small. And some of the features we see in both the high resolution and the CMIP, and that we expect too, are these rising cloud tops, meaning a positive feedback in the long wave, and the reduced anvil area. That will give a negative feedback. But we also actually see here in this model, we see a core thickening. So that kind of compensates a little bit. So the rising cloud top is the dominating effect here in the tropics. But we also see reduced subtropical cloudiness as expected over the broad stratocumulus regions, although closest to the continents there is some increased cloudiness, giving a negative feedback. In the mid-latitudes, we see the expected phase shift feedback, so this negative feedback when ice goes to more liquid. So much is similar, which is reassuring then that even these coarser resolution models are doing a fairly good job. But we also see indication of rather large quantitative differences between ICON, this model we're using, and other available global storm resolving models. There aren't so many, but there are a few that we can compare. So there's more further scrutiny is required here, and maybe climate modeling comparison projects with these high resolution models will be necessary too. So the projected feedbacks, they're also in line with the cloud contributions to the observed energy imbalance trend. And we have already heard, and we will hear more from Gunnar about EEI, but the short version here is that instead of an energy balance that we have in an undisturbed climate, when the incoming solar radiation is balanced by outgoing thermal radiation, we have, because of the greenhouse gases, the situation where the Earth is not able to emit long-wave radiation fast enough. We have an accumulation of energy in the system, mainly in the oceans, but also in the atmosphere. And this trend, like we've heard, is greater than we can really explain. So what we have done here, and this is work led by Claire Singer and Or Hadas from the same workshop that Sanjim was talking about. What we have done here is that we separated contributions to this EEI trend based on dynamical regimes. So we looked at rising and sinking motion and degree of storminess by sea level pressure variability. And we came up with this bar chart showing for annual and for the 4 seasons, the contributions from the different regimes. So in addition to the clear sky effect in the purple here, the tropical ascent, which is actually, the long wave and short wave effects of clouds there, they pretty much cancel. So this is a clear sky effect, just the greenhouse effect of carbon dioxide and water vapor. But aside from that, we see that the northern hemisphere and southern hemisphere storm tracks, the gray sections, they contribute about a quarter to the total trend. And so does this subsidence over ocean and subtropics do. So another quarter there. So together, storm tracks and subtropical subsidence regions actually account for approximately 50% of this trend. And the storm tracks, it has to do with this shift towards the poles. And in the subsidence regions, it has to do with loss of clouds with warming. And with this separation of contributions, we can use this to test models, and we can also use it to kind of think about what this EEI trend will do in the future, because we know then what contributes and how will this continue in the future. And it looks like there's reason to believe that the trend will actually continue. And with that, I actually want to move to aerosol-cloud interaction, because human influence on climate is not limited to greenhouse gas warming. Human activity, including fossil fuel burning, also gives rise to aerosol particles in the air. There are natural aerosols, of course, but with anthropogenic activity, there are many more aerosol sources, as this cartoon here indicates. And those aerosols, they interact with radiation directly, they scatter and they absorb, and they also interact with clouds. So each cloud droplet is formed on an aerosol particle. So you can imagine if you have more aerosols, you can create a cloud with more and smaller droplets, just because you had more nuclei to form these droplets on. And a cloud with more droplets is a brighter cloud, so therefore it matters to the radiation budget as well in climate. So looking at this cartoon with all these sources of aerosols and all these different processes that they are involved in, maybe it's not surprising that we can't yet quantify all of this perfectly yet. And the radiative forcing from aerosol cloud interaction is in fact the most uncertain forcing component still. And one issue when we calculate aerosol forcing is that it is done relative to a reference pre-industrial climate. And knowing the pre-industrial aerosol composition and amount, that's not easy. We can't go back to the pre-industrial and measure. And there are indications that we actually underestimate the pre-industrial aerosol. So, for example, this study that we did where we used the Southern Ocean, the remote Southern Ocean, as a proxy for pristine pre-industrial conditions. So the Southern Ocean is far away from anthropogenic aerosol sources, and because aerosol lifetime is short, aerosols fall out or rain out of the atmosphere in about a week's time. Not much anthropogenic aerosol is transported to this remote region. But there are still aerosols there, though. So there are sources of natural aerosol from the Southern Ocean. There's sea salt, but there's also particularly new particle formation from biogenic precursor gases, especially during sea salt melt. So that's what's illustrated here in this figure. And we found that climate models typically underestimate this Southern Hemisphere aerosol. So here are satellite observations in black, and the red and the blue are an ensemble of climate models. And over the Southern Ocean here, we see that these models are not able to capture this actually pretty large amount of, this is droplet numbers, so the aerosols form droplets. And an underestimate of the pre-industrial state could of course lead then to an overestimate of the anthropogenic aerosol forcing. Another problem is detecting an aerosol signal when background meteorology is hard to control for. There's so much variability in meteorology. And this brings me to another way where I worked with ROM. I wasn't in INDOX, but I was in CARDEX, Clouds Aerosol Radiation Dynamics Experiment, that was conducted in the Maldives in the Indian Ocean. So we made use of the observatory that Örjan talked about, MCOH. And this was in 2012, so you can tell that some of us are younger than we are now in the picture. But the monsoon off-continent wind here is very stable. We went through in the wintertime, and it brings aerosol to the cloud field in the Indian Ocean. So it's a really good spot for us to look at aerosol-cloud interactions. And we found, one thing that we found, was that black carbon aerosol absorption of solar radiation, suppressed turbulence, and that led to a warmer and shallower and more humid boundary layer or surface layer. So we see here in this figure composites of more polluted and cleaner cases. So the red are more polluted cases and the blue are cleaner cases. And we see that in the polluted case, it's warmer, it's also more humid, and the top of the boundary layer is lower than in the cleaner case. And then that resulted then in clouds in the polluted case reaching higher, poking up out of the boundary layer more. So to the right here, we see composites again are more polluted and cleaner clouds, and the taller clouds in the polluted case. So we found this by having UAVs, drones flying and measuring clouds and aerosols and turbulence and combining that with satellite data. And we chose this site for CARDEX because of the stable meteorological conditions. And sometimes we talk about natural or opportunistic experiments where aerosols are changed in an all else equal setting, and there really is no all else equal setting for meteorology, but in a region close by, this CARDEX regions, there's actually something like an opportunistic experiment going on, because there is a shipping lane in the Indian Ocean where restrictions in fuel use has caused a drop in sulfur dioxide, SO2, and SO2 is a precursor for sulfate aerosol. So this image here shows this shipping lane, this is SO2, so we see that where the ships have gone, there's a lot of aerosol. And there have been studies indicating changes in occurrence of lightning over this lane. And one might think that should relate to the deep convective clouds there. So Tanisha Garg, a student at Stockholm University, is working on this and finding that even in this relatively well-controlled environment, it is hard to find a signal. For shallow convective clouds, she can see a shift towards more cloud fraction, especially in the smaller droplet sizes, and also a shift to smaller droplet sizes in general. And that gives an enhanced reflectivity in the lane. So here is effective radius of droplets, and here's longitude and latitude. So this is the shipping area, and here's what the satellite can see. And then she's constructed this counterfactual where there's no shipping, and you can see the difference where the droplets are smaller over the shipping lane. And Tanisha has then calculated the forcing that this gives rise to, finding some contribution from the smaller droplets, but the largest contribution from the cloud fraction increase, actually. Looking at deep convective clouds, though, and tracking individual systems, comparing those developing in the shipping lane and in a reference region, there is some indication of the cloud tops from the lane being higher, but that signal is weak. And I note too that we have to use a pretty sophisticated statistical method to get this signal too, so to create a counterfactual to get a significant signal. We can also use machine learning more generally to separate aerosol from meteorology, or at least to indicate the relative importance of the two for cloud property variations. So we have shown that just a simple gradient boosting regression model can be used to reasonably well predict a microphysical cloud property like droplet radius from meteorology only. So for a range of different regions that are shown in this map here, we create this simple model to predict droplet radius, just giving a lot of meteorological data to a machine learning model. And we see here the degree of explained variance there, the R2 for these different regions, and we see that our model does best in the stratocumulus regions. We get an R2 of 0.6 or something like that. And although the expectation is then that more aerosol, all else equal, results in smaller cloud droplets, we find in this case that adding aerosol information as input data to this model gives very little improvement to the model actually. So if you compare the filled and the open little circle here, that's the difference that the aerosol made in this case. And even actually the sign in some regions of the aerosol influence on cloud droplet effective radius was not the expected one. So I guess this speaks to the difficulty of detecting unambiguous aerosol signals and showing us that there's hardly such a thing as all else equal in terms of meteorology. So having emphasized uncertainty and difficulty in detecting a signal in a noisy background, I think it's interesting to relate to the discussion of actually using aerosol cloud interactions for deliberate climate intervention in terms of what we call marine cloud brightening. And this is discussed often with ship tracks as an observable analog. So ship tracks are clouds brighten in areas where there is shipping aerosol. So this is over a stratocumulus stack, and you see these lines, and that's where ships have traveled and added the aerosol there, and the clouds have then had more smaller droplets and become brighter. So the reasoning is typically that since we can detect ship tracks, we could create similar effects of cloud brightening by adding sea salt aerosol to the cloud and making them brighter and then cooling the climate. This isn't something that we can easily experiment with in the field, or maybe should even experiment with in the field if we could. But in a model, we can add sea salt, as shown here for 3 subtropical stratocumulus regions. And you need a lot of salt, I can say that, something like 50 teragrams per year to get a forcing comparable to the greenhouse gas forcing. And interestingly, but maybe not surprisingly, the effect you get depends a lot on what model you use. So what I had here, this is a simulation I did with NORISM. NORISM is one of the models here. It's the green line, I think, but then there's a bunch of other different models here, and this shows then the cloud shortwave forcing as a function of the mass flux, and you see that there's quite a large spread there, I think a factor of 6 or something like that. And even in the direct forcing, so the clear sky effect, basically there's some spread but less. So yeah, that's just an example of how the uncertainties in aerosol cloud interaction and forcing related to it and the poorly constrained representation in models can play out in an application like this. I should say for marine cloud brightening that there are, of course, also uncertainties related to detectability, efficiency, saturation, heterogeneously distributed climate effects, side effects, ethics and governance, not least, that have to be taken into account. So my very briefly summarized take on this for now is that these things are important to think about what this would entail, but it's hardly something to rely on, and plan A to reduce emissions to bend the warming curve is the obviously necessary thing to do. But I hope that we can maybe get back to this in discussions on resilience and solutions later in the week. So in conclusion, I'd like to emphasize that clouds play a key role in climate change and estimates of climate sensitivity. Total forcing is uncertain due to uncertainty in aerosol cloud interaction. Feedback is uncertain due to uncertainty in cloud feedback. So we really need to keep studying clouds and their interactions with climate. And our toolbox is broadening, for instance, with these storm resolving models and with machine learning methods. But as Ram has said today already, he told you he doesn't trust the models, right? He'll say, we need the data, look at the data, get your hands dirty with the data. What do the data show? Of course, combinations of in situ and remote sensing data on short and long timescales are crucial. So with that, I would like to end again with a thank you and a great big congratulations to Ram.